So let me start with a short video, and I'll explain it afterwards. And it has audio. You may not hear it, but let's try. Okay, that was a short clip from a video that I sent out to a few friends when I was working on this project. And one of my friends is a composer and an audio expert. So an hour later, he sent back an email with his audio track that he made using his own Foley system. And I was delighted by it. I thought it was funny. And you may have noticed that that little creature, as it was walking, was staggering and stumbling and trying to stay upright. Or at least it looked like it was trying to stay upright. It wasn't really trying. It's just made of software that's putting pixels on a screen. But the fact that it looks like it's trying, I think, is very interesting. And that's because of the genetic algorithm. Now, a few things about the vestibular sense. The three semicircular canals of the inner ear are roughly orthogonal to each other in terms of the axes that they are aligned on. And this apparently natural selection preferred it that way. It's tightly coordinated with eye movement, with nystagmus and various other systems in the body. Proprioception is also important for balance and equilibrium. It's a hugely complex system, but it goes pretty much invisible to us. We don't really notice it. It's when it works, when we're healthy and everything, it works just fine. And it's mostly invisible, and you don't know what you got until you lose it. And so when I got a terrible case of vertigo many years ago in Kyoto, of all places, I became very appreciative of this complex system. So there are definitely more than 5 senses, and vestibular is one of them, and it's highly coordinated with other senses. Now, some background, one of the models for walking that is often used is the inverted pendulum. So you plant your foot down on the ground and that becomes a fulcrum for an inverted pendulum, and your hip is the end of the pendulum. This assumes a stiff leg, and there are some researchers who believe that this doesn't really cover much. There's a more general system that uses a spring mass system. It's a compliant leg model, and this is being explored by robot engineers who are looking at spring mass systems for modeling robotics. There are a few people who are looking at developing vestibular systems as well, but I can only scratch the surface on this because it's not my area of expertise. This is more like where I'm coming from, simulated evolution of locomotion. And so there are several examples of work that's been going on. One of the first examples here is Sim's blocky creatures, which actually I presented a paper at the same conference at MIT in ALIFE2023, I believe it was. And there have been several interesting variations, including some recent soft body work, including this delightful animation, a walking creature, and here is a swimming creature, all developed with evolution. So, and of course, there's a soda ray soda constructor, which many of you are probably familiar with, two-dimensional toy simulation, and the springs change lengths according to sine functions. And so that's what I'm doing here in 3D. So spring physics, you got a bouncing ball, you connect 2 bouncing balls with a spring and you get this linear object. 3 balls and 3 springs makes a flexible triangle. And then 4 balls and 6 springs gives you a tetrahedron, a wobbly tetrahedron. The tetrahedron is the simplex of the 3rd dimension, and it's a very useful component for building structures such as the ones that I'm using. So morphology does not, anatomy does not evolve in this system, the topology specifically. But the proportions can change. Those are genetic, and the genetic algorithm does evolve some of the proportions. And I started with the top row, the tripedal creatures, where they're initialized on 3 point masses. And I wanted to kind of get everything working with the tripeds before moving on to the more difficult challenge of bipedal locomotion. And so here's a quick video of some of the tetrahedral creatures. These are some of the tripeds, the evolved ones, and here are some bipeds, the hopping tet, and so on and so forth. And this last one here is 5 tets, and it's 5 tetrahedra and 18 springs and 8 point masses. And that's basically a simplification of a creature, an animal like a chicken: a head, a tail, a body, and 2 legs. And here's an animation of that creature walking on its pointy feet. Now it's following this red dot, and notice that this red dot, it's blue, dark blue, and then it turns red when the creature is close to it. And at that point, this red dot, which I call the target, is moving away. It's evading the creature, and it's also moving randomly to keep things fresh. And the creature is able to turn towards it. And the reason the creature is able to turn towards this target is because of a sense organ, if you will, that is able to detect the direction to the target. So an influence in this work is Valentino Breitenberg's vehicles, where concepts like sensor and actuator are used in this experiment. So every creature has a heartbeat, a base frequency that determines the gait period. If all of the springs change at the same rate, the creature would pulse like this, very unnatural. But they are genetically different from each other. So their phases and amplitudes of their sine waves are different. If the phases and amplitudes of the spring oscillations are random, you get this crazy motion. And this finally is an illustration of how the tilt sensor, this green line, is able to send signals through to, and they're genetically determined as far as how they change the phases and amplitudes of those sine wave, so those oscillating sine waves in real time. And that's what the genetic algorithm optimizes for. So these springs are like scaffolding to put sensors and actuators on. So this makes them embodied, and they're embedded into the creature. And this is an illustration showing the direction vectors in global space that are determined by these springs in the body, and how they are compared to the directions of other things in the world. So here's an illustration showing a direction vector in space based on that spring. And as a vector in global space, it's compared to points in the environment. And I use the dot product to determine how the differences in that direction. The zenith is used for the tilt sensor. It's in the opposite direction of gravity. And that's what the vestibular senses is based on. So on the left here are 18 sine waves of an unevolved random creature, and in the middle is an evolved creature's sine waves. The amplitudes have calmed down, and some of them are quite flat. And over here on the right, there's a bit of bumpiness in these sine waves, and that is showing the effect of the sensors, which are in real time responding not only to the points in the environment, but to the wobbling of the creature's own body. So here's that wobble as shown as a red line. And the red line is really what the genetic algorithm, what is being selected for in evolution. I don't have time to get into the details of the simulation other than to say that I used as few constants as possible, as I could, to keep the simulation simple and sleek so that I could focus more attention on the modeling of the vestibular response. Influenced again from Valentino Breitenberg, in a paper that he wrote in Artificial Life in the 80s, I believe, where he's interested in the idea that the brain has a naive sense of movement, even though the body of the creature of the animal could be very complicated with lots of articulation, unlike his vehicles, which are like chunks moving in space. So with that idea, abstracting away the gnarly details of bodily movement, I am just looking at the end effectors, these black points at the bottom of this diagram where it makes contact with the horizontal surface, and the rest is not so important, is that they can move on these points of contact. I was going to base it on opposing muscle systems, but decided to go even more abstract than that. So the genetic algorithm uses a population of 100 creatures, 100 individuals, and they are evolved using 3 components of the fitness function. And those components are as follows. The blue line here shows target fitness, and that component of fitness is based on how close the creature is to the target on average over its lifespan. The green line shows the upright fitness component, which is how long the creature remains upright before it falls on a point other than a foot. Fine, the feet can be bouncing along the ground as long as fine, but if another point hits the ground, the creature dies, simulation stops, and the duration of being upright is fixed there. And then finally, the red line is a penalty for excessive spring force. So for instance, if a creature's springs are fighting each other, causing large oscillations, then that creature will have a lower fitness. The GA parameters, this is described in the paper. I think it would make more sense in the context of the paper, so I'll just move on from that. Here on the left is a top-down view of the target. So at initialization, the creature is here in the middle, and the target is initialized in a random position on the circle. And it's initialized randomly so the population doesn't get in the habit of moving in one direction. Keeps things fresh and it helps to avoid overfitting. There's lots of observations. One observation is that the sensors, the directions of the sensors were not in the perpendicular orientation as I had expected. And I think in the case of the tetrahedron, the reason that it has this weird behavior is that there are not that many degrees of freedom in the tet. So it kind of hops along an edge with the, the reason the green sensor is the way it is, anyway, it's explained in the paper. But this tetrahedron was not very good at turning, as you can see on the right picture there. Sometimes the ability to move, to have locomotion is stronger than the ability to turn, and those are two things that have to evolve together, and they don't always get it. Here's finally an illustration, a video of walking on undulating terrain, a bumpy surface.
1 minute left, sorry.
Okay, all right. Well, this is the last bit, so I'll just end there and we'll take questions.